Okay, continuing with our discussion of the symmetric slab. In the last slide, I wrote down the phase matching condition for both TE and TM waves. Right now I'm going to focus on just the TE condition. So this is the phase matching condition for TE waves. And I gave a quick sketch of the tangent function. Here I'll make another sketch of the tangent function and try to give you a picture of the solution that will emerge. Okay, so here's what the tangent function looks like. It has multiple branches, okay, as follows, and I'll just draw the first couple of them here. What this phase matching condition does is it gives us solutions for those waveguide modes which will propagate. Okay, so here's the waveguide. Here is a single zigzag ray undergoing one complete period inside the waveguide. Okay, so this is a complete period. And the condition is that the phase change here is a multiple of 2 pi, where m is an integer. Okay, and this phase matching condition gave rise to this equation. So what we're going to do is we're going to sort of assume that we're going to fix the indices n1, n2, and the zigzag angle. And we're going to ask ourselves what thicknesses of the waveguide, d. It actually turns out that every time we get the term d in here, we get the ratio d over lambda. And that comes from hd over 2. H has a lambda in the denominator, so we end up with the d over lambda combination here. We're going to find those values of d over lambda that provide for this particular zigzag angle to propagate, that is, to satisfy the phase match condition. Okay, so we're going to take the right hand side here. Let me call this term the right hand side, and we're going to go ahead and say, okay, whatever its value is, we've fixed n1, n2, and theta, and we're going to find its value here on this vertical axis. So here's that value of the right hand side. In order to solve an equation like this, you normally have to do it graphically because of the transcendental nature of the tangent function. And so what we're going to do is we're going to go ahead and strike this value here and find this first solution. Okay? And this first solution we're going to call hd naught over 2. Okay? And we're going to say, okay, that characterizes a particular thickness of the waveguide for which phase matching occurs. Now what I'm going to do is I'm going to take and look at what these other solutions are, and we'll figure out that they correspond to different thicknesses of the waveguide, or different values of d by lambda, which also allow for this particular zigzag angle to be a valid solution. Okay, so what I'll do is I'll say that tangent of x of any x is equal to the tangent of that x plus m pi, where m is an integer. Okay, and so that's to say that if this value is a solution, then this value is also, and that the distance between these two in this plot is pi. Okay, so what we'll do is we'll suppose that hd naught over 2 satisfies the equation. Then we're going to say that h d naught over 2 plus k pi also satisfies. Okay, that makes sense. And what I'll do then is I'll write this term as follows. First of all, I'm going to plug in for h, and I'm going to write h d naught over 2 is, let's see, the 2's cancel, and I get pi n1 d over lambda cosine theta plus k pi. So I'm going to evaluate this, and now what I'm going to do is I'm going to say, look, n1 and theta were fixed. And so I'm going to factor them out as constants. And so I'm going to write pi n1 cosine theta, and then write, let's see, I've got d by lambda, d naught by lambda, plus k over n1 cosine theta. Okay, this is the result we're looking for. So what this shows is that if h d naught over 2 satisfies, then this value also satisfies, and this value can be written like this. In other words, if I take the dimensionless quantity d naught over lambda, they both have units of meters, and I can find a particular waveguide thickness for which this fixed theta provides a phase-matched solution, then I can also find another value of that unitless quantity which also satisfies it, and it's given by this. In other words, I can write a sequence of solutions to this. Given that very first solution, I can find all the other solutions. So in other words, I can write down, let d naught over lambda be the, and I'm going to call this the dimensionless waveguide thickness. Let d naught over lambda be the way that solves the phase match condition. Then d naught over lambda plus k all over n1 cosine theta also solves. And we'll say for fixed n1, n2, and theta. Okay, so this is the important result, and it turns out this is the result only for the TE waves. Okay, it turns out that the TM solution, which happens to be the same equation except with this plus pi over 2 in it here, you can see that the whole thing is shifted pi over 2 over. In other words, it's shifted over just half of a notch here. And what happens is that the solutions for the TEs fall on these spots here, and the solutions for the TMs are going to fall in between those places. Okay? And so what we'll do then is we'll write then, including TM solutions, we have d naught by lambda plus k all over 2 n1 cosine theta. And now I'm going to, instead of calling that k, I'm going to call it m, where m is an integer. Okay, and when m was 0, 2, 4, when m was even numbers, we had the TE, and when m was odd, we had the TM solutions. Okay, and so this is the important equation that we want to derive. Okay. Now we can interpret this equation and say that we can say that for a particular waveguide thickness, or for a particular theta n1 and n2, we have the mth solution to d over lambda. So we're going to call it the mth solution is going to be d naught over lambda plus m delta d over lambda, where delta d by lambda is equal to 1 over 2n1 cosine theta. Okay, and so these give the other modes. So these multiple solutions yield multiple waveguide modes. Okay, and I'll continue with the discussion in the next video.